We present a novel algorithm that creates highly variable characters, which we call chimeras. In this example, all 4 creatures are bare-legged. A diverse set of chimeras with different running motions are learned from a running motion of a bear. As the chimera motions are physically simulated, the chimeras can interact with the environment, such as getting hit by balls and stumbling down. From given source motions and characters, we can create a chimera in a part-assembled motion, which we give as an initial guess. The border color of the character shows which source character each body part comes from. Our controller learns the best spatial and temporal alignments, while preserving the style and the semantics of the source motion. Generated animations include appropriate physical effects. Motions of body parts from the same source motion can also have different temporal alignments. Here, the forelegs and hind legs of the dinosaur follow different time warping functions. The fore and hind legs learn to swing in opposite directions, even though the initial time alignments were given the same. Characters with large differences in limb length and weight can be combined into a chimera. In the part-assembled motion, the contact time of the both feet is the same, but through physics simulation, the contact time of the heavy foot becomes much longer. We reproduced N-leg walk from the walking motion of a humanoid. The legs between each character were said to have twice the weight of a single leg. As the number of legs increases, the frequency of the gait cycle increases and the stride becomes shorter in order not to fall. The distances traveled by N-leg humanoids are significantly slower than a humanoid walking on 2 legs. Our algorithm is able to create animations of a chimera in a grotesque form, such as a character composed of 2 upper bodies of a bear and 2 lower bodies of a dinosaur. Each upper body and lower body have different time alignments. The front legs move first and then the rear legs move by slightly dragging its feet. This chimera consists of the same source character and motion as the previous character. The difference is that the 4 legs are positioned in a straight line, and each leg has a different timing function. The time alignments of the legs of this chimera are completely different from those of a previous one. We created a centaur whose arms of the upper body have different timing functions. The centaur can recognize information about the environment through the height map and can traverse uneven terrains. In this animation, arm swing of human walking is reproduced. We also learned the centaur's running motion. Unlike walking motion of a centaur, the swing phases of the arms are synchronized to match the phases of the front legs. The centaur can run on terrain with large height differences. The centaur also learned to jump over obstacles. We created a chimera with 6 arms. Arms connected to the same body on different sides form a pair. 3 pairs of arms have different timing functions. Each arm rotates in the opposite direction to the arm on the same side adjacent to it. We created a centipede-like chimera from a human leg. The chimera has 9 pairs of legs, and each pair follows a different timing function. The chimera moved each leg in a different time alignment to move forward. The long spine of the chimera have no source motions, but it curves naturally, drawing an S-curve. Our algorithm also works for motions other than locomotion. Ride is a part assembly of 8-leg horse jumping motion. The part assembled motion, which preserves style but is not realistic, is modified into physically plausible motion by the dynamic controller. We created a humanoid chimera with a T-Rex tail who can attack with his tail. Part assembled motions are spatially and temporally be aligned to satisfy the goal to hit the target strongly. The bare-armed humanoid has the bear's right arm transplanted on the humanoid. The upper right shows source motions of the current Chimera animation. It is equipped with walk, run, attack motor skills. It can steer while walking and running. Various hybrid forms of motor skills are possible, like attack while walking, attack while jumping, and attack while running. This example shows how locomotion and aperiodic action can be combined and synchronized in our algorithm. The truant consists of the right-left arms of the humanoid, 2 front legs and 2 hind legs of the horse, and the torso. The torso has no source motions and responds freely to limb movements. The truant is equipped with 4 motor skills including walk, punch, kick, and jump. The walk motion is generated by combining horse galloping and humanoid walking. The kick motion is taken from the horse kicking the hind legs. The punch motion is taken from the humanoid punching. Each source motion was properly transplanted in the learned animation of the truant, which has completely different body structure. We validate the effectiveness of our algorithm by comparing it with baseline algorithms. We separated the humanoid character into 2 body groups, the right leg and the other. We intentionally set initial time alignments where both legs move back and forth synchronously. Our algorithm successfully recovered natural biped gait with its 2 legs alternatingly swinging. The baseline algorithms result in hopping motions because the partwise phase alignment is impossible in both algorithms. We checked whether our algorithm works the same way in the running motions. Both legs move back and forth synchronously in initial time alignment here as well. Our algorithm successfully recovered natural biped running motion, while 2 baseline algorithms failed to even learn a hopping motion. The horse character is set up to have 5 body groups, the torso and 4 limbs. Each body group is assigned with an individual face. Our algorithm reproduced the initial animation at low speed. As the target speed increases, stance paces become shorter and the trot gait is discovered. The gait cycle of a natural trot data and the motion generated by algorithm is very similar. B1 generates the motion with increased stride length, but it cannot satisfy the target velocity. The motion generated by B2 satisfies the target velocity, but the gait pattern is same as walking. The Chimera has the body of a T-Rex and 6 humanoid legs. In the initial animation, all legs on one side simultaneously swing forwards. Our Chimera learned to move 3 legs simultaneously while having the other 3 legs in contact with the ground, like a tripod gait of an insect. Baseline algorithms generated motions that follows the initial timing, which is unstable and wobbly.